All right, so today we're going to focus on two objectives in this lecture. It is to define aquifer types and water table dynamics, and then to explain how heterogeneity and anisotropy impact water flow. So first, we're going to talk about this idea of different types of aquifers. We're actually going to play with this a bit in our class. But what we're taking a look at here is we have, first let's define the aquifer types we have and how we may know a little bit about these aquifer types. So the first one at the top, which is called a water table aquifer, or is called an unconfined aquifer, and is an aquifer that is at the surface here, right? And that is oftentimes following the topography of our system. So you kind of get an idea. And this water table aquifer is going to easily be able to interact with incoming precipitation and will change as a result of these changes in things like precipitation taking place in these environments. In comparison, a confined aquifer, which we have below, or sometimes these are called artesian aquifers, are separated from the atmosphere itself. And they're actually under increasing pressure as they move under what they call an aquitard, or a confining layer. These confining layers are oftentimes things of very densely packed clays, right, that don't allow a lot of water to transition between one aquifer into another. And as this aquifer here, at this point in time, it's actually unconfined. But as water flows through the system and it continues to be separated from the unconfined aquifer up on top, it has increased pressure exerted on the system, right? All of that water is essentially stacking up on the system itself. And so when we drill wells into these artesian aquifers or into these confined aquifers, what we see is that, for example, in this one, you can see that when we compare it to where the water table is, right, designated by this upside down arrow, we put a well that's in here, we actually see that the water level in this well that drills into the confining unit is exerting that higher pressure, and you see a higher water level in that confined system compared to the unconfined. Now there are options, or not options, but there are occasions where this confined system can have such a degree of pressure on it that when you puncture through the system to put a well in, the actual water table is so high, because you go back to here, and this is what's essentially setting the pressure dynamic for the confined system back where it's unconfined. So we see that the water table is actually able to up and come over this. And so it's trying to reach up to this point. And so we call these wells flowing artesian wells. So they're located in a confining unit, feeling quite a bit of pressure. And that pressure had been controlled by when the system at some distance far away is being recharged by the atmosphere. So an example of this is it would be considered in South Florida, where we have the Floridian aquifer that is recharged near the top of the panhandle, but persists at significant depths out all the way to southern Florida. So if you install a well that goes into the Floridian down there, you actually can get these artesian flows coming out of them as well, because of that long increased pressure that happens as a result of these confining layers. Now, there's a lot of questions you're going to ask about your system when you walk into it. And you're trying to think as both a geologist and a hydrologist about how this is going to impact water flow in your system. So a question you're going to really want to understand is, what is the degree to which your material is all the same? So we may call that homogeneous, or whether that material is heterogeneous in nature, meaning you have all sorts of different kinds of materials potentially mixed together in a system. And the reason that we want to understand that is because they have very important implications for what's taking place in terms of the overall hydrology of this environment. So let's take a look at first this homogeneous case. If your material is all the same, and let's say that this is all sand, you're going to have infiltration that's similar across all of this environment. And your vegetation will likely have similar abilities to pull up water from there as evapotranspiration. So we're fairly homogeneous in this system. And because of that, the groundwater, the water that recharges the ground and potentially groundwater flows are going to be much more homogeneous in this instance. And infiltration is going to be dependent more upon what's on the surface than necessarily what's in the subsurface, since they're all the same. Now, conversely, in a heterogeneous environment, we may have differences in our materials, such that we have materials with a low hydraulic conductivity and a high hydraulic conductivity. Where our hydraulic conductivity is low, we have less ability to necessarily infiltrate water. We may produce more lateral flows in these systems, and we will have lower recharge rates that take place in these environments. Or conversely, if our hydraulic conductivity of our materials increase, we have the ability to pull more water down into the subsurface. And so you can imagine, right, that the degree of recharge that occurs in your environment goes from something that is very low to something that is very high in these environments. So understanding the degree to which your subsurface units are homogeneous or heterogeneous will impact the way that you think about water flow in the subsurface. So let's think about what that exactly might look like here. So on the top image, what we have is one entire unit of just sand. Where conversely, on the bottom, we have a heterogeneous or layered material. We have a silt layer on top of a sand layer. We put a well in and we inject a dye into the system. And we can see this kind of very nice homogeneous spreading that takes place in the sand where everything is exactly the same. Conversely, when we put this well into this layered system, we begin to inject the dye or the contaminant into the system. We see that the sand, which has a higher hydraulic conductivity, is actually able to transport that contaminant or that dye much further along than what we see happening in the silt unit with a much lower hydraulic conductivity. So again, understanding these are going to help us to understand how a plume may be moving in the subsurface. Now, depending on the type of the distribution of the material and the directions of flow, we use different types of methods for determining the average hydraulic conductivity of an environment to use for calculations. And I'm not going to go into these in great depth right now, but just for you to know that there are different ways for us to do this. And in the future, we're going to actually see how these get applied in different manners. So the other thing that we have to think about is the isotropy of the system. So isotropy is telling us what is the variation as a function of direction. So when we think about our systems in the subsurface, right, we have to always continue to think about them as if they are in 3 dimensions, right? So we have the ability to move laterally, we have which is both in the X and the Y, and then we have the ability to move vertically, which is in the Z direction itself. So if you can easily move, if water can easily flow in the X, Y, and Z direction, it's considered isotropic. But if there's a preference for the direction of flow, like you see in the right-hand image here, and that preference of flow changes with direction, we say that that's anisotropic. It is anisotropy or anisotropic. So with those, what we have is, for example, in this one, we have this kind of more platey type of potentially clay material or a shale in a system. And so we see that in the X direction, there might be ability to move the water more readily. Well, in the Y and Z directions, there's less ability to move water in those directions. So if we put these ideas together, we can have both differences in heterogeneity as well as differences in isotropy. So on our top column, we see that the materials are heterogeneous. One is a layered system, and the other one you could think of as, a mixed up area where maybe it was laid down by potentially riverine activity, like lots of cobbles put into the system. And so we have differences in the heterogeneity of these environments. The one where we have the layering in the system, we may have differences in the ability to create flow in the X direction versus the Z direction. Or conversely, even though we do have these areas of lower hydraulic conductivity in the upper right-hand image, they're equally spread out throughout the entire unit. And so water in both the X and the Y direction, or the X and the Z direction, is the same, and so it is isotropic. Conversely, in the bottom image, we have an entire system which is homogeneous. It's the same types of material, but we could have differences in the isotropy of the system as a result of something like fractures. So here we may have fractures in the X or the Y direction that are enhancing flow in comparison to the other flow directions, where conversely in the system adjacent to it without the fractures, we see that the flow may be similar in both the X and Y direction.